The difference between a procedure and an experimental or methods section is that a procedure is a list of instructions. This is what you're supposed to do, whereas an experimental is a list of observations. This is what you actually did. And so you have to be, if you just title it procedure, that's fine, and you wrote what you actually did, that's good. But if you write a list of instructions, add this to that, or that's not necessarily.
You care if you had
I don't care what you title it, but in the future you should title it experimental.
You care if you had an analysis versus discussion?
If you wrote analysis versus discussion, that's fine too. Discussion is just an analysis section, but you're going against convention. Everybody knows what a discussion section is, and whereas analysis could be different. So that's fine. I don't really care about the headings that much, but in the future you should try to conform to the standard headings.
So we don't have to write out a procedure, just three-dimensional, what we did on the computer. We have to have that.
No, what it is it's the procedure is what you read before doing the experiment. The experimental is what you read after doing the experiment, because what actually happened. What actually happens, I'll tell you what actually happens. This is very common in lab, and that is you never follow the procedure exactly the same as it was written. I mean, I've never done an experiment where I've followed the procedure to the exact. And so what you do is you're always modifying the procedure as you're going along, and then you've got to make sure that you record those modifications to that. And so the procedure might say get 20 milliliters. Well, I don't want to spend hours trying to get exactly 20.00 milliliters. It's a waste of time. So you just get something close to 20 and then write it down, how much you actually got. Okay. And so a procedure would say get 20 milliliters. An experimental section said, well, 19.95 milliliters was obtained, or 20.32 milliliters. Some people might get a dropper and get it right on the drop. It depends on what you're supposed to do. With a pipette, you're supposed to get it right on the drop. All right, were there any questions about this report? What to do for the next one? No? I'll tell you, these kind of reports get easier and easier to write as you do more and more of them. No, just whatever you can finish, just do it. I just want to see if you're on the right track or not. That's all.
So let's do Tuesday?
Yeah, let's do Tuesday. Just turn in what you have done. It's okay. There's no minimum number of pages. Oh, do Tuesday or Thursday? Just turn it in next week. It's okay, any day. This is not worth any points. You could turn it in Tuesday or you could turn it in Thursday. I like to collect them on the same day so I don't get them mixed up and lose them. And that's another thing. Another thing to be careful of is never give your original data or your original work to anybody. You always keep a record of that in case it disappears. And so some people might give me all their original data for an experiment, and I lose it. And then what record do they have that they actually did the experiment? Anyway, it defeats the purpose, because the whole idea of a report is to give it to somebody so that they can keep it forever. You don't say, "Oh, give me back my report." You usually just give it to them, and they keep it. But I'll give you this one back. The other reports as well. All right. We're going to continue with Chapter 20 and this lab here. But let's talk about
Just we just turned in the crystals. Do you ever announce a winner of that thing?
oh, I have a winner. I calculated and I was going to post it on Piazza, but I completely forgot to do that, and so I'll do that. Winner. There's the crystals. Actually, this semester, a lot of nice crystals, and so that was good. Let's compare. In past semesters, you get a lot of like just pasty crystals that look wet and they're highly contaminated. But this one, a lot of big, nicely formed crystals, which is good. Crystal growing is actually pretty hard. I was working for years trying to grow nice crystals of different substances to put those into what's called X-ray diffractometer to get the structure of that. And to do a proper this is called a single crystal X-ray analysis, you need a crystal about 1 millimeter big. And so I was trying to grow these crystals, and I kept getting crystals smaller than 1 millimeter, a little too small to do. And so then I started reading about crystallization. And then the crystallization is somewhat of an art form because how there are certain things you can do, right? And I did all of those things, but still you get small crystals because you get too many nucleation sites. This is nucleation and growth, and I know there's a lot of people who've talked about that in their report, which is great, to talk about. But and so it's very difficult. Finally, I did get one big enough, but then I started reading books about crystallization, and apparently I went out and I got this this Russian book, The Art of Growing Crystals by a Russian chemist, and so I thought, well, maybe I can learn something new there. But by the time I got that book, I had finally succeeded in growing the crystals. But it was hard. I did so many recrystallizations. Try to get the purity higher and higher. Anyway, but those are nice crystals there, that's for sure. And so I still have the prize for that. I hope to announce that. I'll announce it soon. All right. Last time we built the cell with the SHE, and so you should know what the basic SHE looks like. The SHE, when we do things with the SHE, we'll just put the SHE on the left, regardless. And let me show you what happens. In the last case, we used. Did we do the SHE? Okay, we drew it out. And we hooked it up to what? The chromate, dichromate? Okay. All right. We're going to take the SHE again. SHE consists of what kind of electrodes? Platinum. And H plus at what concentration? 1 molar. And then we're going to bubble hydrogen gas. Literally, you hook up a cylinder of hydrogen and you bubble hydrogen onto the surface of this platinum. So the hydrogen comes into contact. And the hydrogen gas is going to be at 1 bar/atm. And so this will be under standard conditions. Now, let's hook this up, not to what we had before, but we're going to hook it up to a zinc electrode this time. Zinc solid. And we want to do this under standard conditions. So if I have a zinc electrode, zinc's a pretty reactive metal. What should I put in solution here? Well, in this case, I'm going to put Zn2+. And I'll put this at 1 molar. And so now we have kind of a tug-of-war for the electrons. I need some kind of salt bridge in here. I'll just label it the salt bridge. Probably sodium chloride would work fine here. Just use that. Now, we're going to kind of have a tug-of-war. Under standard conditions, this is a tug-of-war. It's going to be 1 molar H plus versus 1 molar Zn2+. Who's going to win? You have equal numbers. And so if there's a tug of war for electron, H plus versus Zn2 plus, who do you think will win? H plus. In fact, this is a reaction. You know, H plus will dissolve zinc metal. And so H plus is a stronger oxidizer than Zn2 plus. So H plus wins. If the H plus wins the tug of war, which way do the electrons flow? The electrons are going to flow backwards, right? What we call backwards. If we have my voltmeter stuck on here, it's going to read a minus voltage here. Do you know how many volts? Well, it's going to read a negative voltage, so we call the voltage E. And we'll call this E of the cell under standard conditions because we are doing it under standard, which is E of the reaction, you know, or the redox under standard conditions. And this is just the what we call the anode half potential plus the cathode. What happens at the anode? Oxidation or reduction? The anode is where we generate electrons or consume electrons? Generate. Remember, it goes A to C, left to right. Electrons are generated at the A, the anode. And so we generate electrons at the anode, which means what reaction? An oxidation reaction happened or a reduction reaction happened at the anode? Oxidation. So oxidation happens at the anode, and at the cathode we have reduction. And so if H plus wins this tug of war, then who's being oxidized? Well, normally, which way? On the left, normally we write what? On the left, we write anode or cathode on the left, by convention. On the left, we write the anode. The anode is where the electrons are being generated, right? On the right is the cathode. At the cathode, the electrons are being consumed. This is by convention. But in this case, which way are the electrons flowing? The electrons are flowing right to left, which means the H plus is consuming electrons. And so we got 2H plus 2 electrons is going to generate hydrogen gas here. And so the H plus are pulling the electrons and consuming them. That means the electrons are being generated over here. That is, the Zn solid must be being oxidized to Zn2 plus 2 electrons here. And so things are flowing backwards. Right. Okay, so this is by convention. You know, by convention, this should be the anode. And if this were the anode, the electrons should be generated. So H2 should be going to 2H plus 2 electrons. That's the proper anode reaction. And over here at the cathode, we should be consuming them. And so Zn2 plus should be consuming the electrons. So Zn2 plus 2 electrons yields Zn solid. And so by convention, the net reaction is this. By convention, the net reaction is H2 gas gets oxidized by Zn2 plus to produce 2H plus Zn solid. That's by convention. This is because we wrote it left to right. You know, normally we write left to right. But you know, the voltage for this, E of the cell is equal to minus, actually, let's see. Does somebody have their redox and acid-base chart handout that I posted on Piazza handy? I had a whole bunch here. They keep disappearing. Oh, okay. You could just keep it. Okay. So E naught of the cell is equal to, all right, is equal to a negative number. tell me what the, can you tell me what the reduction potential of Zn2 plus is? Well, all right. The first thing is we need the oxidation potential for what's being oxidized? Hydrogen, right? What's the oxidation potential for hydrogen? And then we need the reduction potential for Zn2 plus. All right, and so the oxidation potential for hydrogen is 0 volts. The reduction potential for Zn2 plus is
Negative 0.763.
negative 0.763 volts. And so the cell potential is negative 0.763 volts, as written. And so this is going to register minus 0.763 volts. This cell potential means something. A cell potential that's equal to 0 volts means the battery's dead. You know, it's at equilibrium, no change. A cell potential of greater than 0 volts means forward reaction is favored. A cell potential less than 0 volts means reverse reaction is favored. And so the reason we're seeing this is because these reverse reactions are happening. Reverse reaction is spontaneous, is the cell voltage is negative. And so what that really means is that this is not the anode, but this is actually the cathode. And this one is actually the anode here. We're generating electrons. All right. And so what we did was we wrote the reaction backwards. But you know, negative voltage, all you have to do is switch it, and then you get a positive voltage, right? You just, all you have to do is move the left beaker to the right side and the right beaker to the left side, right? Just swap them. And then we get the positive voltage. And so in other words, the conventional right here, this is an error. I should have written this, the SHE on the right side and the zinc on the left side, and then I would have gotten a positive voltage. But does it really matter which side you're on? No. It's just the convention, and so this is why we get these negative voltages like this. The negative voltages just means that when we set up the SHE on the left, it's either going to be positive, that is, we have a stronger oxidizer over here, right? If we have a stronger oxidizer over here, the electrons are being pulled left to right, and the voltage is going to be positive. But we'll get a negative voltage if we put a weaker oxidizer than H plus here, because if there's a weaker oxidizer here, then H plus is going to win, and the voltage will be negative. But you know, the negative and positive is irrelevant, because you know, negative means we should have just swapped it. We should have put the SHE over there. Does that make sense? And so if I just redrew this with the SHE on the right and the zinc on the left, then what's my voltage? Positive 0.763 volts. Do you want me to do that, or does everybody see that? Do it?
You mean rewrite it all?
Rewrite it.
What?
I could rewrite it.
No,
If you want. Yes? No? All right, you've been outvoted. Why don't you rewrite it? You rewrite it and just come up with the net reaction, because the net reaction here is this. We were saying this was the anode because we wrote it on the left. We were saying this is a cathode because we wrote it on the right. And these are the anode reaction, generates electron, cathode reaction, consumes electron. And so when you swap them, then you're going to have these reactions here. And so they should be swapped. That is, flipped around. Are we good with that? All right, the next thing is this. What happens as electrons start to flow? Is the voltage going to stay at 0.763 volts? No, the voltage is going to start to drop. Oh, let me say one more thing about the SHE. Once we have the SHE and we know this, then we could use the Zn2 plus, to figure out any other cell potential. We don't have to. The SHE is a bit of a hassle, right, to set up because you need the hydrogen gas. But the zinc one is easy. And so once we know that zinc is minus 0.763 volts, then we can hook up the zinc to the copper. When we hook up the zinc to the copper, then we can measure the total cell potential and then figure out what copper's half potential is. And so by doing this, then we can generate all the voltages, all the reduction potentials in the table on the handout. And we use those potentials to predict voltages under standard conditions. And so this is what we did here. Okay, what we did here is now I'm going to use copper and zinc. And so here, this is the original cell we built. We had zinc as our anode. Anode generates the electrons. And the anode reaction we want is zinc solid goes to Zn2 plus 2 electrons. Actually, I forgot to do one thing.
What's missing in the other?
The shorthand. Which I'm going to come back and we're going to do the shorthand for all of them. Actually, let's do that right now. Sorry. These drawings are big and cumbersome. So there's something called a cell diagram. And so let me talk about this. A cell diagram, well, this looks like a diagram of a cell, right? But a cell diagram is a shorthand way of writing this drawing. And therefore, if I ask for a cell diagram, I'm asking for a shorthand way. If I'm asking for, I'm going to call this the cell schematic or something like that. Schematic drawing. Sorry. And so a cell schematic drawing will be like this with the wires and the salt bridge. A cell diagram is going to look like this. We have zinc solid going to Zn2 plus, and then there's a double bar here, copper 2 plus going to copper solid. This would be under standard conditions here. So under standard conditions, how many volts is this? So E the cell is going to equal this. It's going to equal E of the anode plus E of the cathode. When we look at the anode, we have a shorthand way of representing that. The anode is going to be Zn solid goes to Zn2 plus, like that. And so over here, we represent the anode like this. This vertical boundary, or this vertical line, represents a phase difference, or phase change kind of thing. So we have a solid phase and aqueous phase. Here we have aqueous phase and solid phase. The double line represents a salt bridge. And so this is the first cell we built here, with the anode on the left, the cathode on the right. And the anode reaction, zinc goes to Zn2 plus, the cathode reaction, copper 2 goes to copper metal. We could write the half reactions like this. At the anode, zinc goes to Zn2 plus. At the cathode, we have copper 2 plus goes to copper solid. And then we look this up. Zinc goes to Zn2 plus is that an oxidation or is that a reduction? This is oxidation. Oxidation always happens at the anode. And so this oxidation means that we have to change it. So this is going to be plus 0.763 volts. And then we have copper. Copper 2 going to copper is reduction. And so we can read that straight off the table. Oxidation potentials, we have to change the sign, right? The reduction potential straight off. And the reduction potential with copper 2 plus is what? 0.340 volts. And then we add these two together and we get 1.13 volts under standard conditions. So we should generate a cell potential like that. So let's take a look at the next cell we built or drew out yesterday. The cell we did yesterday, we put what was it? Iron 2 was the reducing agent. How did we generate electrons in that cell? Iron 2? Yeah. All right. In the last cell we did, we used iron 2 plus, and the iron 2 plus went to iron 3 plus. And so this is the reactant product in the anode cell. Note we use a comma here. A comma is for same phase. And so these would be the same phase because they're both AQ. Correct? And so iron 2 goes to iron 3. What was the electrode that we used? Did we use an iron electrode? We used graphite. Could we have used copper? No, right, because the dichromate would have detached it. So iron 2 to iron 3, and then we use carbon graphite, which is fairly inert. And so here, between the aqueous, we have a phase to the solid electrode here. Double line, salt bridge, to the cathode. What was the cathode? Yeah, we had, what did we have? We had dichromate to, do I use a vertical bar or a comma between dichromate and chromium 3? A comma. This goes to chromium 3, and then what? No, that's not it. We need the electrode in there, which is, we use the gold electrode? Okay. So, the electrodes don't participate in this reaction, do they? Yeah, they just act as conduit for the electrons. That's it. And so do you see the half reactions? Iron 2 goes to iron 3, the other half reaction, dichromate, goes to chromium 3. We should have the acid in here too, but it's all right. We'll leave it off. All right, let's figure out the cell potential. The cell potential for this is the anode potential, which is oxidation potential. So the oxidation potential here is just iron 2 goes to iron 3. So what's the potential for iron 2 going to iron 3? We could look that up. Plus the potential for dichromate goes to chromium 3 plus. And so iron 2 goes to iron 3. What's the voltage? 0.771 volts. Now, is that a oxidation potential, or is that a reduction potential? Oxidation. So this is the anode. Anode is oxidation. Plus dichromate goes to chromium 3, that's going to be the cathode, and that's going to be a reduction. What is the voltage there? 1.33. And this should generate a voltage of, did I miscalculate this? Oh, okay, minus 0.7. Okay. And that should give us how many volts? 0.5. What did I calculate yesterday? 5.9? Huh? 0.56 volts. All right, this is under standard conditions. Now, as these cells operate, what's going to happen with the voltage? It goes down. Okay. And so let's take a look at a reaction here. So just this cell diagram here. And so we're going to talk about non-standard conditions now. And so let's start off with an ice table here. Let's look at the first reaction. Zinc solid plus copper 2 plus goes to zinc 2 plus copper solid. Initial, zinc solid, nothing, right? As long as we have it. Copper 2 plus, under standard conditions, we'll just say 1.00 molar. Zn2 plus, 1.00 molar. Copper, it's pure solid. Okay, let's do a change. You know, because I know the voltage here. The voltage is 1.1 volts, let's say. And let's say 50% reaction. If I had 50% reaction, how much do I lose? Half of it. And so I'm going to go minus 0.50 volts, oh, not volts, sorry, minus 0.50 molar plus 0.50 molar. And so at 50% reaction, I'm going to have 0.50 molar and 1.50 molar. And what is my voltage? Is my voltage, what do you think? Did the voltage stay the same? Did it go down? It went down. Sure, it went down. And so we need to figure out how much it went down. All right. For non-standard conditions, we're going to go back to delta G. Delta G is, this is called the free energy. And what the free energy is this is the total energy available to do work. And so we'll just say energy available to do work. And so if I have like a delta G of minus 2,000 kilojoules, then those 2,000 kilojoules exothermic are going to be available for the surroundings to do work, let's say. That's assuming we converted all to work. You know, we could get some heat as well. All right, electrical work depends on this. The work is going to depend on, well, in electrical work, we're pulling the electrons through the wire or pushing electrons through the wire. But normally the oxidizer is going to be doing the work, right? So we're pulling the electrons through the wire. Well, how much work is it to pull electrons through the wire, or how much work is it to suck water out of the hose? Well, it depends on how much water, right? And so we need to know how much water or how many electrons. So this is moles of electrons. And then you know, are you pulling it fast or are you pulling it slow through there? You know, how much force are you pulling it with? And so the moles of electron, the force is going to be depending on, you know, how many units of charge you're pulling through. And so we have this. We have something called F and E. NFE. So N times F. F is called the Faraday. E is just your self potential or potential. I better write E as self. The Faraday is just the amount of charge per mole of electrons. Amount of charge in coulombs per mole of electrons. All right, if the work is being done by the system, is the system gaining energy or the system losing energy? Let's say. Losing. So if it's losing energy, it should be negative. And so we'll just cite minus NFE. All right, so N times F is going to get us the amount of charge and the amount of charge with some voltage here. And so what we're going to do is we're going to do this. We're going to do delta G, which is equal to minus NFE, is equal to delta G naught plus RT ln of Q. Well, delta G naught is what? Delta G naught would be minus NFE naught. This is for the cell. And so we get minus NFE of the cell is equal to this plus RT ln of Q, which means that E of the cell is equal to E naught of the cell. And so the cell potential under non-standard conditions is equal to the cell potential under standard conditions plus RT over NF. Actually, I want to do a minus, sorry. Just put that in here. Ln of Q. F is, what was F? 99,485? 90,485. I have to remember. Okay, E of the cell is equal to E naught. It turns out that what's the most common temperature we're going to do this at? At room temperature. And so what we're going to do is we're going to fix the temperature. The temperature at 298 Kelvin. And then it turns out that RT over F is a constant. And then we're going to do one more thing. We're going from the natural log, we're going to convert the natural log to a log base 10. Natural log to a log base 10. So, actually, I forgot to look at it. But R is 8.3145 joules per mole Kelvin. T is 298 Kelvin. F is, what's it, 99,485 coulombs per mole. Can somebody verify this for me? Does somebody have their book? I forgot the Faraday, I think. 96 485. All right, thank you. 96 485 coulombs per mole. And so we'll do this. That means RT over F is equal to what? What are the units here for it? All right, give me the number. So R times T divided by F. Point 02 56 7 9. Oh, that's probably enough right now. What are the units? Joules per coulomb. Okay, what is a joule per coulomb? Well, let's take a look at the units here. N is moles. F is coulombs per mole. That gives us coulombs times volts. So coulomb times a volt is equal to delta G is in joules. So joule is equal to a coulomb times a volt. Therefore, a volt is equal to a joule per coulomb. And so the unit, a joule per coulomb, is the same thing as a volt. And so this comes out to 0.025679 volts. Now, how do we convert a natural log to log base 10? Well, you could do the math, but it comes out, we have to multiply by 2.303. Is that right? You guys remember this? Log base E versus log base 10. And so what we're going to end up with is this. We're going to end up with E naught of the cell. All right. And this should be negative because of that negative. Minus, all right, so take this and times it by 2.303, and what do we get? Is that right? I think so. We'll see if it's right when we do this number, when we see the number. Hopefully it comes out to like 0.512. What did you guys get? 0.59. 0.59? 0.0. Okay, 0.059138 volts over n log base 10 of Q. How close did we get? So somebody look up the, this is a very famous equation here. Does somebody know the name of this equation? E of the cell is equal to E naught of the cell minus 0.0591 volts over n log base 10 of Q. This is called the Nernst equation, and it's usually in this form, but one of the restrictions on the Nernst equation is this Nernst equation is only valid at room temperature. There's a Nernst equation at 298 Kelvin because we had to restrict the temperature initially to get that 0.59 volts. Now this will allow us to calculate it. Therefore, at 50% reaction, I'm sorry?
Why does it look like mass lock or something to lock of it?
Because the reason that they convert it to log base 10 is because it's easier to do estimates. In other words, it's easier to do calculations. The reason it's easier to do calculations, what is the log of 100? 2. What is the natural log of 100? You see, so it's easier to do calculations in your head using log base 10, and so that means you can do it quicker. The problems.
If we forgot that number, like when we can do it.
No, you don't have to worry about forgetting because I'm going to give you this equation. The only reason I went through the derivation is because you can't use this equation for any problem, right? You have to use it only at 298 Kelvin. So if the temperature changes, you have to use a different value for this. But it's easy to calculate this value, right? If we change the temperature, let's say we went to 305 Kelvin, then all you have to do is recalculate this voltage, and the calculation is not that difficult, right? To do. But the problem is what do you do with this? 305 Kelvin. We don't have that, do we? We don't. There's no data table at 305 Kelvin. Our data table is at 298 Kelvin. We're stuck. But that doesn't mean it's impossible because you just make a cell. Standard conditions, 305 Kelvin. It's a matter of the voltage. It's your standard cell potential at 305 Kelvin.
Is Z and N the same thing? Because both has Z or
All right, yeah. N because we just usually use that for moles. Z and N are the same thing. N is a little tricky because N or Z, let's just say N equals Z, which equals the moles of electrons transferred in the balanced redox. Equation. So a 50% reaction, Q is equal to the concentration of Zn2 plus, the product, over the concentration of Cu2 plus, the reactant. These are raised to the first power because the coefficient's 1. And so Q at 50% is what? What's the Zn2 plus at 50%? 1.50. And the Cu2 plus? 0.50. So that's our Q 50%. And then we just plug it into this equation. What is N? Two. N is 2 moles of electrons because in the balanced chemical equation, when you look at the half reactions, it's 2 and 2. And so sometimes this is tricky, can be tricky to determine. So be careful. Tricky to determine. All right, so plug this in here. E naught of the cell is like 1.1 what is it, 1.13 volts or something like that. N is 2. Q is this, which is 3. Right? Uh-huh.
Why is it 2?
I'm sorry?
Why is it 2?
Why is N 2? Copper 2 plus Zn solid goes to Zn2 plus copper solid. How many electrons were transferred from the zinc to the copper 2 in this reaction? 2. That's why N is 2. Redox are electron transfer reactions, so you just look there. Or the half reactions, you know, if you're uncomfortable. But the half reactions, you got to be careful because sometimes we multiply those.
What difference? N equals 7 or...
I'm sorry?
Oh,
N equals Z. Yeah. Sorry. It's not supposed to be Z. Petrucci used the Z. And so this would be, Petrucci would call this ZFE. Many books use N. You read NFE. I was just brought up with N. And so that's why I continue to use N. But there's no agreed upon designation. N, because everybody knows N, little n should be the number of moles. PV equals nRT. Okay, tell me what's going to happen. At 50% reaction, did the voltage go to 50% of the original voltage? All right, what's the new voltage here?
$1.115.
1.115 volts. Okay, thanks. E at 50% came to 1.115 volts. So the voltage did drop, but maybe not as dramatically as you'd expect, right? And so if we could calculate the voltage in 90% reaction, 99% reaction, you know, if we'd hit it. Uh-huh. Oh yeah, you're right. We cannot increase the voltage. There's got to be something wrong. 1.08 volts. Yeah, our voltage shouldn't go up. Our voltage should go down.
It did go down.
What was our starting voltage?
1.13.
1.13?
You lost 1C3.
Huh?
You lost 1C3. You started at 1.1.
Okay. All right. Well, anyway, the voltage dropped a little bit, right? At 90%, you'd expect a more significant drop in the voltage, right? And so basically, we can map this out. Now, what we're going to do is we're going to break, and then we're going to build this cell. We're going to build this cell, and what you're going to do is you're not going to hook. Actually, a couple of things. Let me write it down. Do you know what our concentrations are of our solutions? All right. One, you're going to build this cell. Because the concentrations of our solutions are not 1 molar. Our concentrations are 0.1 molar. Straight from the bottle. And so those are actually diluted. And so is this standard conditions or non-standard conditions? Non-standard conditions. So I want you to calculate the E of the cell and build it, and then compare your E of the cell with the theoretical E of the cell. Normally I would expect your E of the cell to be maybe slightly less. Why? The reason it would be slightly less is because what happens is the electrical contacts become corroded. And when the electrical contacts become corroded, we lose a little bit of voltage, transferring electrons across from one to the other. And it's called a voltage drop. And so it would probably be slightly less. Now, if you clean the contacts, then we expect to get the theoretical voltage, right? The other thing is, these solutions, do you think these solutions are standard solutions? You know what standard solutions are? Somebody remind me what a standard solution is. That would be an ideal solution. Ideal solution would be no ion pair. A standard solution is something different, which is remember in Chem 1A you did a experiment called standardization of sodium hydroxide. What was the purpose of that? Standardization of sodium hydroxide. Well, titration was what you did to do. The purpose wasn't the titration. The purpose was you use the titration to do a standardization. So what is a standardization? Or on part 2 of that experiment, you use the oxalic acid standard to make a oxalic acid solution. And so what is a standard and what is standardization? Or have you ever heard of, now it's not called this anymore, but it used to be called the National Institute of Standards, NIST, which is now NB something, National Bureau something and something. But what is a standard? Or you could purchase standard masses. We have a 1 gram standard, which is very expensive. What is a standard and what is this is
Something you
wow.
base everything off of?
Boy, I don't know what to do because I try to emphasize this in Chem 1A with that lab. Standard and standardization are very important vocabulary words. I think I need to have that on an exam. That's what I need to do. At least in Chem 1A, because that's one's really discussed. If you graduate, if you complete Chem 1A and 1B without knowing what a standard is, that's disappointing. Or standardization. You should know what a standardization and a standard is. What do we use the 1 gram standard mass to do? We use it to calibrate our balances. And what did we use? A standard is something that we know the composition to a high degree of precision. And so usually when you're using something like oxalic acid standard, you want to know, what's the composition. Usually it's very high purity, and then we can make things from that. And so standard solution would have a lot of sig figs here. And so these aren't. The standardization of sodium hydroxide is you made a 0.1 molar sodium hydroxide solution in Chem 1A, but 0.1 molar isn't good enough. That isn't high enough precision. That isn't high enough accuracy in that molarity. And so what we did was, yes, it is 0.1 molar roughly, but what we're going to do in that Chem 1A is to titrate it to determine the concentration of that sodium hydroxide to 4 or 5 sig figs. In fact, we got it to 4 sig figs. And then once we do that, then we call it a sodium hydroxide standard because its concentration has been determined to 4 sig figs, rather than just leaving it at 0.1 molar. And so these aren't standard solutions. Nobody's titrated these to figure out, you know, what the precise concentration is. And so you can expect some variation in voltages based on that. But what we're going to do is we're going to calculate E of the cell here. And then 2, we're going to connect this with a jumper wire between the zinc and the copper. And then we're going to time this. We're just going to let it run. You know, depending on the time. A short while or a little longer stuff to do. And then we're going to reconnect the voltmeter. Actually, we need to do this before we use the cell. I said, and compare with the experimental E of the cell. Hopefully they're close. All right, after we put the jumper wire there, we're going to put the voltmeter on and measure the voltage. And so based on the new cell voltage, we expect the voltage to go down. So based on the E of the cell here, what % reaction occurred? All right, we're going to do this, and then you're going to leave this cell set up because I'm going to stop here, and then we're going to do something more dramatic to this. And so we'll go ahead and build this. The amount of time depends on, you know, because there's going to be a backup there. So some people will have a little longer reaction time, some people will have a little shorter reaction time, but don't worry. What you'll do is just record the time, and then we're going to record how much of the battery's been depleted just by, you know, this is like taking a battery at home and then just connecting a wire to the plus and the minus terminal of the battery. What are you going to do? You're just going to short it out, right? And it's going to run. So that's what we're going to do here, just short out the battery and let it run. But, you know, as far as terminals go, what do we call the zinc and what do we call the copper? Which one is the plus terminal? Which one's the negative terminal? What do you think? Is the cathode the plus or the minus? The anode the minus or the plus? What is it? If we're to label one of these plus and the other minus, these are the terminals of battery. So essentially what we're doing is we're just shorting out our battery. We're just connecting a wire from the plus to the minus. And so the question I'm asking is which side is plus, which side is minus? The oxidation side is plus, and the reduction side is minus? Does everybody agree? And so the oxidation side is the anode. The anode, oxidation always happens at the anode. And so we label this terminal plus, you said? Plus is usually given red. And then this terminal minus? It is. It's the opposite. What we do is the cathode is the positive terminal. And one way to remember it is the cathode, is it pulling in electrons or is it pushing out electrons? That's pulling it in. So it makes sense that the cathode is plus. The electrons are going to flow to the cathode, and the cathode is the positive terminal because we got some oxidizer in here consuming electrons. And the anode should be negative because what's being generated at the anode? Electrons are being generated at the anode. And so when you short out a battery, the electrons are flowing from the negative terminal to the positive terminal. And so the bottom of the battery to the to the top of the battery, if you're looking at just a standard cell. And so when we took a voltmeter, the red terminal should go to the copper or the red terminal to the zinc when you hook up the voltmeter. Well, the red terminal should go to the positive terminal on the battery, so the red should go to the copper, the black of your voltmeter should go to the zinc. And so when you look at this, and make sure we just got batteries for this, so make sure you turn it off after you're done. But we have our multimeters up here, the wire should be back there. And when you hook this up, the black goes to what we call the ground. In other words, the middle, if you have 3, and the red should go to the top. Or the volts. No, actually. It's different. We have different meters, sorry. For the yellow ones, the red should go to the top and the black should go to the bottom. Okay. Alright, that's it. So